abnormal things, sort of abnormal things. So now we're going to talk about abnormal normal things. So we're normal equipment, but more abnormal situations on them, I guess. This first one, we're going to go to a nuclear power plant. This is a high-pressure core injection pump. And I told you about Art Crawford, and this was an Art Crawford call. And whenever Art Crawford calls, there's trouble brewing. It's sort of like that other thing. So Art and I have known each other a lot of years, and I was working for a utility, and I did this stuff. I did all their turbine balancing and stuff, and I said, well, I ought to go meet Art Crawford. I'd heard of him, so I went over, drove over near his house, and we actually met in a pub there, and we talked about 5 minutes, and Art said, hey, would you like to go to England for me? So after 5 minutes, he had already hooked me into some stuff, and that was a bad job too, as it turned out. So, but this is my worstest case of Art Crawford job right here, is this one right here. Boy, this one just almost drove me out of my mind. So again, this is, I think he called because I've got a nuclear background, and this is a high-pressure core injection pump. This is a boiling water reactor, and this is one of the pumps that you never run the thing except maybe once a month to check it out. But in case of an accident, you'd need to have this pump in operation so you don't melt the core down, which is a bad thing. So look at the situation that we have here. And boy, this was a tough job. This job about giving me gray hair. We had a turbine, and we have a high-pressure pump, and then we have a gearbox, and we have a low-pressure pump. The fluid comes in, goes from the low-pressure pump over to the high-pressure pump and out. And I don't know whether, most of you probably haven't dealt with nuclear plants, and you're lucky in that aspect. But basically, they have what are called ASME Section 11 requirements for vibration analysis. And in the old days, it was really pretty simple. You took baseline readings, and then if the readings like doubled in mils, then you had to do something. They didn't do velocity, no spectrum or anything. So this pump had been in operation, and its mil level hadn't doubled, so nobody worried too much about it. But then they started doing stuff in velocity, and bingo, 1.4 to 1.6 inches per second on this pump, and that obviously got people all excited about it. So took some readings on it, and the thing is, too, this frequency varies in this. This is a turbine drive, and speed wanders here and there a little bit. So that made things even worse. Also note this 1.987 to 1 reduction on the gearbox. That becomes very important as we move through this case history. So anyway, noted that horizontal and vertical. Horizontal was a lot higher than vertical. Resonance suspension, so did that. So did an impact test, and the main frequency here is right here's running speed, about twice running speed, your primary frequency. Did an impact test. This is the imaginary parts of the transfer function, turbine end, gearbox end of that high pressure pump. And we can see we've got a typical wobble mode here where we're pivoting with the node point in the center. That's pretty typical on pumps, actually. That happens a lot. So I had a natural frequency. This is taking data down, and you can say, well, when we do this in the data, the vibration is high at the edge of the pump, gets down to about 0 at the center, and high in the end, so all is matching. We have a horizontal natural frequency at about 2 times running speed, and everything is matching. So what could be causing 2 times running speed? So we look here and think, well, let's check the alignment. That's an obvious thing. I'm not a big 2x alignment fan, but if you got a gear coupling, it'll happen. But just always remember that 2x is only for gear couplings, diaphragm couplings, and stuff that doesn't work. Grid couplings, that's not what you're looking for. We often say it too much. So I said, check it, and they checked it, and it was like 50-some thousandths out. So I go, wow, that's good news. We're going good here. And just to describe this too, okay, this is like 7 stories under the ground. This thing looks like a chicken brooder. It's got heat lamps all around this thing that keep this hot. This thing has to be ready to go 24 hours a day, 7 days a week. It's hot. They push the button and it goes. So you're 7 stories under the ground. I have probably in this little room 15 people, 2 nuclear regulatory commission people, all kinds of plant people, everybody looking over my shoulder. And I can run this thing 10 minutes, and then it's going to be a month till I can come back because they only run it once a month. So I get my data and said, well, this looks good. We got a high 2x here. We got a 2x resonance. And we now found 57 thousandths out. So they aligned it, and then I have to drive. It's 1,000 miles from home, and I got a ton of equipment, so I'm driving this. So I drive back, and the next month hadn't helped it a bit. Bummer. It's time. Oh, bummer. That's just a bummer. You know. So anyway, I looked at the situation. I said, well, maybe we don't exactly have 2x, but the thing is, the speed's changing all the time, and you can't. It's wandering so much you can't really do a good thing and find out what 2x is. So I decided to use synchronous time averaging. So I can lock in on a pulse that's varying, and then that way I can tell what's what. So I put a piece of tape on here. I did synchronous timer. It went away. It just died.
How much variation in speed were you getting? So that's probably the time that you can't have two.
Yeah, just a little bit, but it didn't hurt it. But it went away. Totally went away. Totally went away. It didn't phase in and out. It just goes bloop, 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 went away. That means whatever's vibrating here at 2x is not phase locked to this shaft, and that's not a good thing. So I'd asked for information, and finally the nuclear plant, for some reason, they don't trust the plant with the information. It's all in headquarters, and I found out, well, there was a 9.87 to 1 reduction on the gearbox. I kept asking, well, how many vanes are in everything? And, well, there's 4 vanes in this pump. I go, oh, man, 4 vanes, 1.987 to 1 reduction. That's almost 2x. That couldn't be, though, could it? So I put a piece of shiny tape down here on this gearbox, measured the vibration on this gearbox, did synchronous time average, it goes bloop, 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 and it stays there. That means the vibration on this pump is phase locked to this pump, has nothing to do with this pump. So did synchronous time averaging on it, and bingo, there's a synchronous time averaging, 25 averages, bingo, it just locks in and it stays there. That means the vibration on the high pressure pump is from the low pressure pump. It has nothing to do with the high pressure pump. The low pressure pump is just doing fine, by the way. But it turns out that when we measured and did all this, that there was acoustical resonance equal to the low pump's vane pass frequency right in this speed range. And we also found out for it would cycle with seasons when we're having a little bit different temperature on the suction water. Everything matched up. And it was actually an acoustical resonance taking the pressure pulsations from the low pressure pump that was exciting a horizontal natural frequency on the high pressure pump. Solution, change the number of vanes from 4 to 5. Took care of it. So that problem sort of goes on. I was doing, it gets even more bizarre, sort of. I was doing a job down in Texas on drag lines, and I had a Vibration Institute meeting in St. Louis. And I had just barely made my flight. I locked the keys out of my car. I had to have somebody break into my car. I am covered with absolute coal covered. I look like this thing that come in off of the street. And I'm going down where's that Union Station there? And I'm walking down trying to get there. I need a bath. I'm looking horrible. And 2 guys are walking from a nuclear plant, and they're talking about the 2x vibration on their high pressure core injection pump and how it's alignment. And I walked up looking like a vagabond. I said, oh no, that's not alignment. You need to do synchronous time averaging, and it's actually a vane pass frequency. And they looked at me like I was from Mars. Like, who is this idiot? And I said, well, just believe me, it's the truth. You'll find out. And it turned out there were several of these plants, and they all had the same problem. And so, but anyway, I thought that problem was the problem that wouldn't go away. Here's a large boiler feed pump, and after only a short period of operation, the inboard bearing of the pump and the seals failed. An alignment study was initiated, and I don't know whether any of you know what Dodd bars are. Does anyone know what Dodd bars are? Oh my gosh. I guess I'm the only one old enough to have used them. These are Dodd bars. They were developed by Ray Dodd of Chevron, and this is before you had lasers and all this good stuff. But anyway, it's a set of bars. You mount a set of bars from this machine. You mount a set, and they have proximity probes, vertical and you can't see them, horizontal. You mount a set of bars on this machine with a set of targets, and then you bring the machine up. If there's any vertical change, the gap closes or opens, and the same thing horizontal, and you monitor alignment online real time. And this was like 25 years ago. So I put a set of the Dodd bars on. It shows the setup right here. And then I watched the alignment. And the thing coasted down, really no problem. And this is a turbine-driven boiler feed pump. And then when they broke the vacuum on it, I had a huge change in alignment. And I had long-range probes. I had 120 probes that were 100 millivolt per mil, which would have a thing. So I actually, when I went out there, they were jammed against it. I go, whoa. So I had to re-gap them and gap them so they take it. Then I had them pull vacuum. I was getting a 100 mil change in alignment when they pulled vacuum on the turbine. So I looked at the foundation of the turbine, and I noted there was even cracks in the foundation. We're going to get back to our friend here I talked about before. So you go down below, and this is the arrangement. You have your main condenser. It's running at about 14.5 psi vacuum. In other words, it's about as close as you're going to get on your vacuum. Then you have piping. Then you have an expansion joint here and an expansion joint here. And then you have these thrust canceling rods that go out here, these really pipes. And then you have this going over the end. And the whole purpose is so things can move around and back and forth. And with these expansion joints, you're not getting any movement of the section of pipe right here, which goes up to the feed pump turbine, because you obviously don't want to do that. So I looked around there, and then again in an observation, again just watching, there was a cover over this expansion. I noticed there was a couple droplets of water, and so the guy said, well, that thing's cracking. You know, we got some very minor cracks in there. And started looking the situation over and goes, well, I wonder what's happening here. And what I discovered was that on these thrust canceling, again, these are big pipes, they have a nut right here, a big, huge nut. And then they have, it's like all-thread rod, and the all-thread rod goes through the nut. And then they can turn that rod, and they can adjust this end cap here and set it so it's wherever they want it. And then whenever you draw vacuum on the turbine, this pipe's under vacuum, and the atmospheric pressure pushes here. It then pushes into the all-thread rod, into the nut, and down these things. And that way, whenever you draw vacuum, all the vacuum force goes into these rods, into the side of the condenser, rather than being applied to the pipe right here. So I looked, and I noticed the machine was down. I noticed the all-thread rod that the threads were sort of flattened out there. And what I finally discovered was the nut on the inside of here broke off. So whenever we draw vacuum, now this all just moves in, and the pressure from the end here goes right to this pipe. It just squishes. And when it goes to this pipe, then you've got a 20-foot pipe that goes up here to the turbine. And I did some calculating here. It has a 60-inch diameter pipe. The area, pi r squared, is 2,827 square inches. You take that times 14.5 psi, is 41,000 pounds of force pushing this way. The length right here of this pipe is 20 feet. That's 820,000 pound-feet of torque. That's basically all being applied right here to the base of your turbine whenever you draw vacuum on this. So the question is, what do you do? Well, being a farm kid, I said, why don't we just put the nut on the outside, weld it on the outside of the thing instead of the inside? So that's what they did. It just basically, I don't know, it's sort of idiotic putting the nut on the inside. Put it on the outside, and when you draw vacuum, the nut pushes against the end instead of possibly pulling against the weld. So anyway, that was a sort of a very simple solution, but a very complex problem that it took the Dodd bars to see this huge alignment change, then going down and actually visually looking and seeing what was going on down there. So again, amazing, 820,000 foot-pounds of torque, and you can see why it cracked the foundation and just moved that big turbine around. Okay, solution, put the nut on the outside instead of the inside. Okay, go to a circulating water pump. These are large vertical pumps, and they pump water through the condenser at a power plant. And they're having trouble tearing these things up. And this is an old reading. What's this? 1980. I have indeed been doing this a long time. This was an old IRD 350 with a strip chart thing. And this is just a broadband vibration, basically broadband vibration. Here's one thing that pops up here. And I looked at it, I said, well, what could cause broadband? I said, well, if the pump was in a run-out condition, that might do it. So I don't know where I got the drawing. I don't have the drawing here. But whenever I work on pumps, the first thing I'm going to want, unless it's just some bearing or something going out, first thing I always will want, I say, give me a pump head curve. You need to know the flow head curve. In other words, I've got this pressure on the pump, what's supposed to be the flow, what's my best efficiency point. That's where the angle of the fluid coming off the impeller matches the angle of the volutes. There's only one place for a constant speed pump. And if they're not operating at that point, then you know you're going to have vibration and trouble. So this thing was supposed to be operating against 30 feet of head. So I measured it, and it was only operating against 7 feet of head instead of 30 feet. So I got the pump head curve, and the pump head curve didn't even go that far. It didn't even consider. It was supposed to pump 156,000 gallons a minute at 30 feet of head, and at 7 feet it was on past 210,000 gallons a minute. It was just clear off the chart on it. So I wonder what's going on here? How is this happening? So you note right here, there's 3 pumps here, and this is on a lake. And what it is, in the wintertime, the water gets quite cool in this lake. So the operator said, well, these things are a couple thousand horsepower, so instead of running 2 out of the 3 pumps, which is normal operation, we'll just shut 1 pump off. So we're going to shut a pump off, we'll save 2,000 horsepower, and we're doing a good thing here. The problem was the system wasn't designed that way. So if I have 2 pumps pumping in a header, I'm going to create a certain amount of back pressure, and the pumps are setting right comfortable where they want to be. If I shut 1 pump off, then that 1 pump's operating against lower back pressure, and it's flowing like crazy. And what it was doing, it was just eating the impellers up. It looks like you had metal-eating termites, and it was just eating them up, and the impellers were, the pumps were just failing left and right. So it was all well-intentioned to try to save some energy, but in reality it was creating reliability problems. So that's a case where we've got a pump operating against not enough head, and then the flow again. I don't know whether you've ever seen how the pumps work, but you have a tangential component of flow that's dependent upon the RPM, the diameter of your impeller. That's like going along here, like your car's going along the highway. Then you have a radial component that comes out, and that's due to your flow vector. And that's sort of like you're going out the car and you throw a ball out the side of the window. So now the ball is going forward and it's going out, and it actually comes off at an angle. And that angle, whenever that angle, with the outward component is dependent on flow, no flow, high flow, and then that adds to this vector. And so you create an angle that varies from here out to here. And so then your diffusers are set at a certain angle, so only at 1 flow does that angle match. And whenever you get too much back pressure, the flow component drops, the angle coming off the impeller drops, and it's hitting at too shallow an angle, and you get vane pass frequency. And if you have too low a pressure, the flow comes up this way, and you get backside erosion on your volutes and your diffusers, and you end up with runout conditions. So anyway, that's just a basic primer on pumps. But that's why you're getting in trouble. And if you're doing vibration, you need to know where you're at on your pump head curve. Okay. So the next one was sort of the opposite situation. It was a double suction pump. Like this. This is sort of a cutout where the fluid flows in here and it flows out the impeller, and then you got your seals and your bearings here. And in a double suction pump like this, it really should be thrust neutral. In other words, we have flow coming here and here, and everything should be flow neutral. So you have bearings here, and they're not really designed to take a thrusting. They're just designed to just take a radial load. So these bearings were failing on this particular pump about every 6 weeks. And the odd thing is we had 3 pumps here. And on 2 pumps, they run forever. And 1 pump, every 6 weeks, the bearings would fail on that 1 pump. So I took the spectrum analyzer out, and I didn't even take it out of its box. I looked at the pump, and the pump, you can see the shaft jumping back and forth right here, and that's called axial shuttling, and that's a sign that whenever you get a pump operating against too much back pressure, they'll sit there and they'll go, and they'll vibrate. And I said, wow, your pump's probably operating against too much back pressure. So I took a gauge reading on the pump, and the gauge reading on the pump basically said it was in a deadhead condition. It was just basically deadheaded. So I got a drawing of the system and looked, and this pump was pumping like 7 stories up to this discharge tank. And the discharge tank has a control valve, and when the level gets so high, then this valve shuts off, and the pump then goes through the recirc line back to a suction tank. very basic situation. So it had a flow orifice, so you can't just flow back the tank through a straight pipe, or you don't have enough head, and then you'll be running out on the pump. So they had a flow orifice there, and I looked at the flow orifice, and they have a little tab, and it said 2.000, meaning it had a 2-inch hole in it. And I said, well, wow, this is supposed to have a 3-inch hole in the orifice. So pi r squared, that's a lot of difference, 9 to 4. Took it out, had a 1-inch hole in it. So instead of a 3-inch hole in the orifice, it had a 1-inch hole. So basically, whenever this tank got full, this pump was just sitting deadheaded, and then that would cause actually shuttling, and then that would tear out your bearings. So it just, again, you don't always just want to go out and look at your spectrum analyzer. A lot of these things you have to sort of look at what you got, and the pump head curve is just vital whenever you're dealing with pumps. Okay, this is another. This is a broken shaft on a vertical pump, and after the pump had 6 shafts that had broken. It was a vertical pump, and this is an interesting one. I wanted to study this pretty closely since it had so many problems. So I talked to Bentley, Nevada, and actually Bentley, Nevada, and we flew out to Palo Alto, Florida, and we talked to this outfit called EPRI. I don't know, does anybody know who EPRI is? Electric Power Research Institute. Well, I talked to them out there and said, wow, we've got these cases, we've got a pump. We would like to monitor a pump and really do an in-depth study of vertical pumps using XY probes underwater and all that. And we've got one that actually has a problem. We think it'd be a real good research thing. And Bentley says, and we will supply the instrumentation for free. And I said, and I will do the analysis for free. They turned us down. They said, no, we're into computer modeling, and we want to model. I go, model if it's a vertical pump. How are you going to model a vertical pump? You have no loading. Everything goes to infinity. It's bad. You need to do testing. But anyway, they wouldn't listen. So Bentley and we just did it on our own. And Bentley supplied the instrumentation, and we just did it on our own. Instead of the world getting to see the results, they're stuck in Bentley somewhere. So anyway, we did this, and we set up, and this is a typical vertical pump, sort of the curse of the world for vibration people. And we set up XY probes at 3 intermediate places. We put XY casing pickups on the thing. What did I show them? I put a strain gauge with an FM transmitter that transmitted the torsional pulsations, the torsional strain as the pump ran. This was the impeller. I balanced the impeller down to basically ISO 1.0, just as it took me forever. I did it myself, grinding off little pieces. And then I set it up, and I had it drilled and tapped so we could actually put unbalance on the rotor and take it out of the ISO standard so we could get able to run it without, and we had to send a diver down to do all that. I did a ton of work on this. And then we're doing torsional natural frequency tests. We put it in the water so it would be under its normal element. We assembled the thing. We did torsional ring tests on it. This shows where we did that. And we got mode shapes on it, lateral mode shapes. Again, we operating FM telemetry to do the strain. XY probes in the bell. I mean, we did a job on this thing. We set it up to take so we could take orbits. And this is again, put a pulse. Synchronous time average orbit, bingo, nothing. So, in other words, all the motion in this was non-synchronous. And this is what we had. We just had a heap of energy around the first lateral frequency. So the energy was non-synchronous. It was causing stresses in the shaft to alternate in the shaft, thereby causing it to crack. If I have synchronous motion and my shaft spins, you don't cause alternating stresses. But if I have non-synchronous energy, that causes the stresses to alternate. Non-synchronous vibration is destructive to shafts, whereas synchronous is destructive maybe to bearings, but it doesn't alternate the shaft. It all spins around and it doesn't alternate. So did all this work, saw all this stuff, and then started talking to the maintenance superintendent. Probably should talk to him first instead of doing all this work. And I said, what have you done here? I said, these things ran for years, and now they're cracking left and right. And it turned out, I got a picture. It turned out all was this thing. This is a bearing, bronze bearing in the bottom. It's not that it was a source of a problem. It was a source that initiated trouble. So he says, yeah, I needed a new one of those brass bearings, and I went to the manufacturer. New one was $6,000. He says, that's ridiculous. So I didn't buy it from him. I'd made it myself. And he says, that worked so good that when I had an impeller, go out. I just had somebody make that up for me too. I go, oh, why didn't you tell me this? And they said, well, you know, I'm trying to save some money here. So I got with the manufacturer. I told the manufacturer what I'd done. I said, yeah, we've pirated your parts and all that. Everybody does that. But would you work with us on this? They said, sure, you seem repentant. We'll work with you. So they took the impeller up there, and it was off a lot. These are high specific speed pumps. And the angle was off on the blades on the impeller. Everything was just not right. This thing was just set so it was not set to flow evenly, and it caused the broadband energy. And so it turned out we put original impeller back. This never cracked a shaft after that. And he'd done other things too. Besides this, since the shafts were cracking, he was doing self-engineering. He says, I put harder material. I go, that's good. That's really what we need here. And I changed the coupling design too. So he had sort of really done a job on this pump. He's a good guy. He just, you know, didn't realize what he was doing. You start messing with these pumps, you got to realize these manufacturers have spent years fine-tuning these designs. And even though they may look crude, they're not. And they learned a lot of stuff the bad way. So that was the situation. But we did a lot of, used underwater probes. Bentley was great to work with. Got to see that this stuff actually would work. So it was wonderful. So now we're going to go to we're going back to another nuclear plant, and this was a containment spray pump, and these containment spray pumps, if you would have a nuclear, they call them incidents. If you have a nuclear incident, in the U.S., your reactors are all kept in what's called a containment building, which is an awesome building, about 3-foot thick concrete, steel lined, rebar. It can take the reactor and it can depressurize and it'll maintain all the steam. It'll hold it in there. But once you've done that, then you have to spray that steam to condense it, and you spray it with borated water. And so these containment spray pumps, they don't run very often. Again, they just test them. They test them again once every month. So I had noted there had been a problem on this for years. The vane pass was just about to the limit of what the ASME and the NRC would allow. And finally, it got right to the limit, which was 0.7 in this case. So I'd warned them for years. I said, you've got a vane pass problem. You've got 4 vanes in that impeller. You really should change to a 5-vane impeller, and they didn't do it. And then they get in and they get in a bind, and once they get into what's called a tech spec violation, they have 72 hours to resolve the problem or they bring the reactor down. And that's like megabucks a day. So this is another one of those things, if the number of people involved could have solved it, it would have been solved in about a minute. There were rooms of people. And again, they're always looking over and bothering you so you can't get your job done. But anyway, so I did a resonance test on the pump. It's a vertical pump. Did a resonance test on it. Here's your coherence. Here's your phase shift. Here's your response. And we find a natural frequency pretty close to vane pass. This is 111, and the vane pass is here at about 118. So very, very close as we suspected. Turned out, though, it's not like, I know probably a lot of you have done vertical pumps. And vertical pumps generally are in 2 type modes, either the rocking mode if the base is weak, or the first bending mode if you have that. But this one was bending right in the center. This is 120 hertz. And the pump, there was almost no motion. The bottom of the motor, and then this part distorting here was actually the pump casing. And so we're having a distortion in the top of the motor. And this was the mode shape, which was very, very close to the 4 times the 30 hertz speed. So I have maximum at the bottom, actually at the bottom of the motor. So I did some calculations. I won't bore you with too much of this, but basically this is an amplification factor calculation. And basically what you're dealing with here, even though this looks complicated, this tells you how much you're going to be amplified at resonance, and it's dependent upon the speed you're operating at, the natural frequency, and the damping. So really it's only 3 things. You know what speed you're operating at. The natural frequency you can get by whacking it. And you can do a log deck calculation and tell what your damping ratio is. So that's all it takes. It sounds hard, but it's stuff that you guys deal with pretty much every day you can do. So anyway, I found out the amplification factor at vane pass was 5.4. And I said, wow, if I can get rid of this, I can get us way below what the requirements are. So what I decided to do was alter the natural frequency on this by adding mass. And after the mass calculations, if we put in 850 to 900 pounds, that would drop the natural frequency to 101. And I assumed the damping ratio would be the same, and calculated it at vane pass, and it came out 2.5 if I did this particular thing. So they added the 950, and it went from 0.7 inches a second down to 0.26, which was very, very acceptable for this. So anyway, this was a case where we added mass, and this shows the response before the mass was added and then after the mass was added. What happened in addition to doing some detuning, what we used on it was lead bricks from shielding. We had just lead bricks, and they built a platform, very nice platform. They had to do a seismic analysis of this. I mean, it's not like you can just do this. They had to have structural engineers. They had to do all kinds of stuff. But it's amazing what you can get done when you got the heat on you. So in addition to detuning the system, because you have all these bricks that can rub, that added a significant amount of damping, putting those lead bricks in, and pretty much nailed the problem. Okay. This is another case. This is a case where a coupling was destroyed on a steam generator feed pump in a nuclear station. These are the teeth that just totally destroyed. This was the proximity probes, had 5.8 mils of 2X, and this is the orbit. And I'd worked on several of these before, and this was nuclear plants are a nightmare to deal with, even on the non-safety related side. So I told them, I said, well, your alignment is wrong, and they said, well, we're doing what the manufacturer said. Well, I'm telling you, the manufacturer's wrong. I've done a lot of these. And what they've done, you have the turbine, and you think about, well, I got a hot turbine here, and then I've got a pump, and there's a lot of factors that are going on here. The thing that they hadn't considered, and I'd already measured before, I said, well, I've done this before, and when you draw vacuum on those turbines, they'll drop around 20 thousandths, and they hadn't figured that in. And then they said, well, the pump's center mounted, it's not growing. Well, because what you do is you take a hot pump, you're going to grab it in the center, and it grows away from the center, and it doesn't change your alignment. Well, it doesn't, but you've got your supports, and if they heat up, that it does indeed raise it a little bit. So I calculated out, and I said, and your pump's rising, and I said, and the turbine is more than likely probably growing unevenly too. So what they had here, they had set up where they said the turbine's going to grow more than the pump, so boom, they set the turbine here. Okay, they said the pump's not going to grow, but it did. They didn't take into account the turbine vacuum, but it does. So this is the situation they had. So I had them. It took a long time to get these people to do this, and they tore up a couple couplings in between time. But I had them finally change the alignment to setting the turbine low. They set the turbine a little bit high, and then it would draw down, and the pump would grow up, and they never had a problem after that. But it's hard, when the manufacturers tell them to do one thing, and I have to tell them to do another. But then what I finally did, I convinced them. I actually put a set of Dodd bars on. I said, okay, put Dodd bars on, and it took about 3 months to get them to do that. And put the Dodd bars on. I said, draw vacuum, 20 thousandths exactly, just like before. And then the light sprang in their head that, well, maybe the manufacturer isn't taking this into account. So sometimes you deal with that sort of thing too. Another thing, we're going to go into a totally different thing now. This is a generator, and what this is a phase lead off the generator, and this goes 1976. So again, this is getting back here a ways. But these globs right here are molten copper. This is a phase lead, 25,000 volts, 500 million watts, 25,000 volts flowing through this. And obviously it had a problem. There's another hunk of it right here. And this is actually a hunk coming out of the generator. The generator had a phase-to-phase short within the generator, and the generator stopped, according to the oscillograph, in 1/16 of a second when it did this. And it had 24 2.5-inch coupling bolts that just sheared them like butter. Boom! Total lockup and a complete meltdown of the generator. And this is actually where I started. This is a 76. This is when I actually started I started doing resonance testing and things like that. And this shows a shaker on the system. And what we do, we're shaking the coils and note the natural frequency. This is one of them that's having a problem. Basically what I did, I went in every year after this and I tested all the phase leads. These were 2 Westinghouses, and they kept having problems come back, not blowing up, but we were catching them early this time. And the natural frequency is 126 hertz. That's cold. As you heat the unit up, this will actually drop, and that causes you to operate right on 120 hertz resonance. And then the phase leads actually sit there and they shake. And when you take the unit apart, you take the end bells off, you can actually take your finger and rub next to these, and the fiberglass would turn into like a talcum powder, yellow stuff. And I used to test these every single year. Here's a mode shape of one. This is 82. I did a mode shape on that. And what you're looking at right here, this is fiberglass. They actually put fiberglass pieces in here, and then they bind that, and then they put it in resin. You feel like you're rebuilding a car body or something in there. That's how they did this stuff. And this is where I'm having to stiffen up one of these that did it. We bring special people called winders in to do this. And these things would loosen up. It's a really poor design. And I got very good at this. There were 2 units, and you can take the end bells off, and I could actually just go up there and just lay my hands on all 12 of these, and they'd say that one, and that one will be bad. And they would be, because of the sympathetic vibration from the other unit, you could feel them buzz. They thought I was exercising demons or something, but just feeling that vibration from the other. And then you do the impact test, and it would verify it. So just a little bit of history on some weird stuff. Okay. So we're going to go into even more weirdness. I don't know whether I've been blessed or cursed by this business, but I seem to always end up with this weird, odd stuff. And this was a turbine, and a 500 megawatt turbine, and they would shut it down. They'd be going along, they'd have a problem, and it would trip. And if they started the turbine back up, it would start up fine. But if they waited more than a couple hours, you couldn't start it back up. You had to wait, a couple days to start it up. So if you didn't start it back up within 2 or 3 hours, you weren't going to get it back for 2 days. And I've got, besides a mechanical background, I got a nuclear engineering background, and that sounds like xenon poisoning to me. That's what happens in your nuclear reactors when you shut them down. You have a buildup of xenon. Xenon is one of the decay products, and xenon is like a neutron sponge. When xenon is present, you ain't going nowhere for a while. That's why the Navy reactors, besides length, the Navy reactors enrich their uranium about 90%, whereas our normal reactors are about 3%. The Navy reactors have enough reactivity that even if they've got xenon, they got enough oomph, because you can't obviously shut down and not go for 2 days. But anyway, I said it sounds like xenon poisoning. There's something in here that's coming in and going away that's affecting it. The vibration was right here, so I did an alignment. I said one thing that could cause this, so I knew the problem was oil whip. That's oil whirl that locks onto the natural frequency of the rotor. And here's running speed, and when this stuff would come in, this was what I was seeing. This is 6.15 mils. This thing's just about ready to trip. Here's a map plot. The thing would go up, and when you would start it up, you would get to like 2,700 RPM, and then this stuff would come in, and even though you brought the speed up, the frequency of the whirl didn't change. And what that is, it's the oil whirl is oil whirl, but whenever it locks on the natural frequency of the rotor, it's called oil whip. So even though you bring the speed up, it stays at the same speed. So we had oil whip. So I set up this system I'd read about in Canada, and basically it's a system where you mount these T's upon a bearing, and then you have this plastic pipe, and then you go into copper pipe, and then basically if this T raises, then there's a little float in there. I think I show a picture. Then if the T raises, then this float with a disc on it, a metal disc, drops. So sort of imagine it this way. This T raises right here, boom. The ethylene glycol, just antifreeze fluid, flows out. The little deal drops, and you change the gap. The gap changes. So I tested this out in the lab. This is my lab setup. And what I did, I had a shaker here. I put a 60 hertz signal, the stimulated setting on a machine running 60 hertz. Then I throw in some DC, and then I've got a dial indicator up here, and I throw in enough DC on my shaker to raise, say, 0.003 of an inch on the dial indicator. And then the fluid would flow out, the little float thing would drop, and the probe would measure the DC gap difference, and it worked great. And the Canadians had an idea, and it worked good. I altered the idea a little bit. But anyway, this would allow us to check the alignment, because you can't use lasers. They didn't have lasers in anyway in those days. But you couldn't get in here to see the bearing. It's hidden in behind valves and things, and you can't see what's going on. So this shows one of them mounted in here and back behind the hood. And this is just mounted through here. And then again, if this raises, the fluid flows out and all that. So what I did, I modified the Canadian design, because I said, well, yeah, but what if the glycol heats up? That's going to swell it up, and how are you going to tell? What if I get a leak or anything like that? So what I did is I put another probe outside, and then I used that as a reference probe, so anything common to the system, like heating up glycol or leaks, would thereby affect this probe the same as it did. Then I just subtracted this probe from the other, and all I would ever get that away is any change just due to that probe alone. So anyway, I did that, and we drew vacuum, and wow, you know, when you draw a vacuum on a big turbine, they move a lot. That's what we found out. And that's okay. I don't care as long as the whole turbine drops, but the problem is the one bearing dropped more than the other. It dropped 16 thousandths more. In other words, the bearing that was going into whirl dropped 16 thousandths more than the high pressure bearing, which doesn't set on the condenser. So that was one factor. So I said, yeah, but it does that every time. So the key factor, though, was, let's see if I can see it. The key factor, though, was this is a big HP turbine. The steel is about this thick on it, 2,400 PSI. It's a hunk, you know. This is a low-pressure turbine, thin shell wall. So what happens when you shut it down is this cools down much more rapidly than this. So we have two factors. Then we have the condenser drawdown, which is lowering this bearing. Then if you shut it off, in a 2 or 3 hour period, this one drops significantly. That gets enough misalignment going to whirl. If you wait 2 days, both of them get cool. And see, so as a factor then of that, so what we did, I had them change to actually a tilt pad bearing, and I don't know if I got a picture of that or not. Yeah, I had them change to a tilt pad bearing, and there's an outfit called Centratec out of Houston. The president of Centratec, this is his first big turbine bearing. He actually came up and installed the bearing. So we put a tilt pad bearing in there that didn't care that we misaligned it. Because there's not much we can do. We're going to have condenser drawdown. We're going to trip sometimes. And you say, well, why don't you just set that bearing high? You set that bearing high on turning gear, you're going to wipe it. See? You're sort of took here, you know. So I just had to put in a bearing that didn't care. And then this shows you right here, running speed component went up a little bit because the tilt pad bearing has different damping characteristics than a regular bearing. But this sub running speed, it just eliminated it entirely. No longer did we have to deal with that. And I calculated the cost savings on that. I don't normally do that, but the cost savings on that, because we had about 2 or 3 of these incidents a year, it was horrendous. It paid for the bearing each time that happened. This is a chiller turbine, and it was destroying bearings. This is actually a chiller right here, and this is the turbine and the chiller. It was destroying bearings, and the odd thing, they were beating up the top part of the bearing instead of the bottom part. And again, I used the Dodd bars, and I checked the alignment, and it looks like right here as you go, the turbine drops. So I saw an expansion joint, again being burned by these expansion joints. I said, wow, you know, as we go, we must be drawing vacuum and the turbine must be dropping. So I put dial indicators across the expansion joint. I drew vacuum, absolutely positively no movement at all. This turbine was braced, and when you drew vacuum, it had no effect on it at all. So I go, oh boy, that's weird. So I said, well, if it's not moving, the compressor must be moving. So I mounted some lasers on it, and I shot across from the bearing over to an I-beam, and then what was happening was this was tilting back. It's like the compressor was tilting back like this, and that was pointing up there, and that caused it to make it look like the turbine was dropping. So anyway, I wondered what was happening, and then I found there's this huge heat exchanger here, and then there was this pipe here which didn't have an expansion joint in it, and this pipe would chill down to, because it was a chiller, it would chill down to very low temperatures, so when this shrunk, that would pull this compressor backwards, because this heat exchanger was 10 times as big, it wasn't moving, and that would cause the compressor, and it's very repeatable. Every time it did the same thing. So what I finally had to do, I actually took the turbine and I had to set the turbine in the air, and the back end of the turbine, because I have to set 120 thousandths high. And they've ran like this. They always have me come in and align that thing. And again, the manufacturer's alignment recommendations were entirely wrong because they didn't they had no way of knowing this was happening. And you have to set it up high. Okay. Well, let's see what this is. Oh yeah, it's an odd one there. Okay. But anyway, that's just another case where sometimes if you're having these issues with bearings or couplings, you might need to do an online monitoring system. And you can say, well, I'll shut it down, I'll put the laser on. That doesn't do any good. Things happen too quick. I checked one the other day, and guys, in a half hour, by the time you got your hold cards and everything, you get a lot of movement is what happens, a lot more than you might think. And in this case where you got vacuum, as soon as they take vacuum off or something else happens, it changes too much, so you need to monitor things online. This is a very peculiar one. This is a compressor, one of these big compressors in an air liquefaction facility. And we had this 4 times the input shaft appeared on the proximity probes. And describe these a little bit. I don't know how many of you worked on these. I've seen entirely too many of these in the last year. I never want to see one again, ever. But they're motor, and you got 18 or 3600 RPM motor. And then you got a big bull gear in here. I mean, it's a big old bull gear. It has about 200 or 300 teeth on it. And then it's driving pinions that have your high-speed compressor elements. They're only about that big. So I have, on one of my high-speed components, it runs, 10 or 11,000 RPM. I've got 4 times the input speed on that. And it just doesn't make any sense, but it's enough that it's tripping the unit. And it turned out, this is another one of those observation things. When I went, they also, off this bull gear, they had an oil pump that was being driven on it. It was just cantilevered out. It was running 3 inches per second, the oil pump was. Is a natural frequency problem again. That oil pump, its drive was translating across the bull gear, and that was actually shaking the high speed pinion at that. And it was merely to stop it temporarily. I just drove a 2x4. I drove a 2x4 in between the oil pump and the casing, and the vibration on the high-speed pinion came down. The only component was the high-speed pinion component. Again, some of these things you sort of go out and you got to dig around and look and see what you can do. Okay, this shows right here that's going along. I installed the brace on the oil pump, and this is the first stage high-speed pinion vibration. I put a brace on the oil pump. I take the brace off the oil pump. Bingo. And very peculiar. Okay, you're going to talk about a thing called the Lomacon effect. A lot of you probably know about that. This is a large pump. It'd operate for a year or so, and then the vibration would start to creep up. This happened time and time again. After the overhauls, the pump would operate okay for a few months, and then they would bring the 1x running speed vibration on the pump would go up. They'd bring the rotor out, and it'd be balanced the same as when it went in. No change in balance, but yet the change in synchronous motion would go up significantly. I did a peak hole plot of it, and you can see right here, what's this going to be? When I bring my RPM down, look how the vibration drops. So what are we operating near? What would be operating near if the vibration changes a lot when you come off speed? What? Resonance, natural frequency. How come it wasn't there to begin with? There wasn't a natural frequency there when we put the pump back together. And this happens again and again and again, and when we take the rotor out, the imbalance hasn't changed. So what have we got? We got something called the Lomacon effect. I mean, what that is in pumps, you have a rotor with no seals. These are just your bearing stiffnesses. But on these big high-pressure pumps, you have interstage seals, and a lot of them. These interstage seals begin to act like bearings. They put a lot of stiffening on your rotor. And this stiffening is a function of the pressure and the flow. And so basically, as you increase the flow and the pressure across these seals, that increases the force of the seals on the shaft. It's just sort of like taking a guitar string and vibrating, you putting your thumb in the middle of it. It has a tremendous effect. But once these seals start to get a little wear, you lose that stiffening effect. And once they lose the stiffening effect, you're now operating on the rotor's natural frequency. And these are a hard thing to find. You know, somebody says, well, I'll do a resonance test. You'll never find it on the shaft because it's not even close to what it's like when it's in there and when the fluid is flowing. You can model your bearings, you can model your shaft, and it's still not going to give you the right answer because the effect of the seals is enough on these high pressure pumps that has a stiffening effect on the rotor. And as long as the seals are good, that stiffening effect is there. And if the seals start to wear, it starts to go away. And even though you have the same amount of unbalance, the response to that unbalance becomes much greater. It's called the Lamican effect. Some people call that a reverse mass effect. It's really strange, all the different things you do it. This is a high-speed compressor, and this was a nightmare for somebody. I got in on the tail end, fortunately. They had taken this compressor apart 3 times, 2 times local shop, and then they finally sent the compressor back to the manufacturer, and they stack balanced it, which means they balanced the shaft, they balanced each component individually, then they'd put each component individually on and they'd retrim it out. And they sent it back, bingo, still high vibration, 3.8 mils of vibration, 7,000 RPM. So I got to get, this is another Art Crawford. This is another Art one. I'm thinking these Art Crawford things, there's nothing good about them, I can tell you that. But this is over around where Art was at. So anyway, I watched this. I watched the thing. I did a plot as it went up and down. And when I went up, I go through the critical speed. There's just a little blip there, not much. But then as I go, it does what Ed Gunner calls a moonshot. It just, okay? So if you've got unbalance in the rotor, then my natural frequency is going to respond at the natural frequency. I didn't get any response at the natural frequency because meaning the rotor is very good. But what this does represent is if I have overhung unbalance, this is just how it'll act. If I have overhung unbalance, it'll go through and you won't necessarily get much at the natural frequency, but it just keeps going up and up because this little section right here is acting like its own little independent rotor, and right here is where your prox probes are at. They're very sensitive to picking this up. And so I said, well, I think you've got overhung unbalance, and I put a weight in it, 23.7 grams, and it dropped down to 0.6 mils. From 3.8, and I just put it in the coupling, and they had spent, I am not even sure how many tens or hundreds of thousands of dollars ripping this thing apart 3 times, and it was all just because it needed like a washer in the coupling. And they're now religious. When they take the coupling out, they have a little thing there. It's sort of funny. It's a solid mounted thing, and it's got 1 through 12 in it. And they take each coupling bolt, nut washer, and they put it there. And everything is match marked, and they just religious about putting their thing back together. Because if you take a high-speed compressor like this, turn 15,000 RPM, and you get unbalance in the coupling, which is an overhung mass, they're extremely sensitive to this. And then you put in the fact that your prox probes are right here. Those prox probes are going to be reading that, and you have to be very, very careful in that situation. I've done a number of these. I had one I only added 4 grams. So a little bit of review here. We talked about the vacuum across an expansion joint causing 820,000 pound-feet of torque. Again, you got to watch those expansion joints. Oil whirl and whip caused by vacuum drawdown. Melted phase leads caused by resonance. Incorrect alignment calculations, not taking everything into effect. Cold shrink and piping caused an alignment shift. Vertical pump, where we had to add mass to the motor to change the amplification factor. Broken shafts, mainly because the guy had bought pirate parts. Then this wrong size orifice causing pressure pulsations, axial shutting that started the bearings. And then vane pass from one pump vibration causing a vibration on another pump. I think a lot of these things, if you look at a lot of these situations, you cannot solve these by looking at a spectrum analyzer. You can't solve them sitting at a desk. You got to go out there and you got to get dirty. And you got to talk to operators. You got to talk to maintenance guys. You got to dig around and go out. I most of the time look like a filthy thing from a garbage dump, because that's the only way you find a lot of this stuff out. Okay. Part 3. We're going to go to motors and fans now. How much time do we have? Am I running out of time? Oh, boy, I'm going to have to move on this one then. So we're going to have to scoot on this. Okay, I ran into this a number of times. I don't know how many of you work on these large fans, but a lot of these large fans, they'll have a Babbitt bearing, and then they'll have it's mounted in the housing here, and then on top of it they have this big bolt called a plunger bolt. And have you seen those? Yeah, you've probably seen what I'm showing here. Then, oh man, these will nail you. I had this happen last year again on a major fan, and the plant personnel had been trying to balance this, and they were getting nowhere. And these are pretty good guys. They're good balance guys. So I didn't try to balance it because I said, I trust these guys. If they're having balance trouble, then there's another issue. So even in all these modern days of digital everything, I still carry this thing called a shaft stick around. I carry a shaft stick and I carry a strobe light because, you know, you just need that stuff sometimes. And I usually have this little box with prox probe that I can set up because you got to have this stuff to do these things. So anyway, there was 2 mils on the casing, but when I took the shaft measurement, there's 17 mils. Well, there's only 8,000 sparing clearance. Well, that don't add up. That dog won't hunt at all. How are you getting that when you only got 8,000 sparing clearance? There's only one way, and that's if the bearing's loose in the housing. That's the only possibility that you can have here. I said, the bearing's loose. They said, did you tighten that plunger bolt? And I go, no, what's that for? I go, that's what holds the bearing in the housing. You tighten it down. So they tightened it down, and the vibration went up to, it rose actually to 21.5 mils when they tightened that down. And after that, we were able to just balance it. So why can't you balance this situation? Because it's what we call nonlinear. This is highly nonlinear. All your balance, whether you're using plot and vectors or using these programs and your calculators, are all based on linear response. In other words, I put in 1 ounce, I get 1 mil of effect. I put in 2 ounces, I get 2 mil effect. I put in 8 ounces, I get 8 mils of effect. Well, when I've got something losing the housing, that don't work no more. It doesn't work at all. You'll run your tail. You'll just chase your tail for days. You'll never get it balanced. So you have to get it to where the system, there's no looseness in the system, so you create a linear system. Or I don't care if you got a Cray supercomputer, you're not going to balance it because it doesn't have the things that you need. So anyway, I still like to carry a shaft stick, and I've got my 2130, and I've got IoTech, and I've got everything, and I still have a shaft stick with me, and I still have a strobe light for other reasons too, because I like to look and see if keyways are missing and all kinds of stuff that goes on out there. Okay. This one, high fan vibration on the motor, and this is I was working out in New York City on the skyscrapers. And boy, if anybody would ever make some money, they ought to go do that. I wouldn't live in New York City for all the money in the world. But there's a lot of business out there. They have these skyscrapers you cannot believe. They will have a couple hundred air handler units, pumps. They got to get the water. They got tremendous. I went to Rockefeller Center and down 2 or 3 stories down. They have pumps. They're like boiler feed pumps to pump the water up to the top of those things. They have a tremendous amount of equipment. They know nothing. They know nothing out there. Zero. They were balancing fans, and they were saying, I said, well, how do you balance fans? And they go, well, we put a weight on, and we got this thing to do a strip chart, and if it gets better, we add more there. And I go, don't you do phase? They go, no. I go, oh. So I balanced one, and they go, wow, that's a miracle. I go, no, it's just the rest of the world. You're just, nobody decent in vibration is going to live out here, sorry. But most people, vibration, they live out in the country, and they work places, and they don't want to live there. So anyway, I helped them out for a while. But I started going around, and I kept having the same problem. And I go, somebody's doing something wrong in New York City. I don't understand these people at all. So I have a fan here. I wish you could see a little better. It's not too bright. I got a fan here. I've got isolators. They're all on isolator screws up and over there. And I've got a motor. Okay? So I go and I measure the fan vibration, 1650, and it's very low level. But I go to the motor in the vertical direction, I have 15 mils at 1650. Well, they thought that was motor unbalanced because they had this little strip thing and it didn't have enough resolution to tell between the fan unbalanced motor. I said, that vibration on the motor, that's in the fan. Oh, they say, it is? They said, we keep sending the motor out and it doesn't get any better. I go, duh, no wonder. It doesn't get any better, it's not that. So anyway, I had quite a time out there. It was very much of a cultural conflict. I was standing on a corner and I had my stuff, and this guy come by and he tapped me on the shoulder and he says, welcome, welcome, stranger. I said, is it that obvious that I don't belong here? He says, yes. So, so anyway, but back to the story. You always have to have a little humor and work with these situations because it's odd to deal with. But anyway, when I found out the isolated natural frequency under the fan was 700, but the isolation natural frequency under the motor was like 1620. I go, what is that?